report for Lab 3, magnetic field of a bar magnet. The purpose of this lab was to help visualize magnetic fields, observe the relationship between the distance and magnitude of the magnetic field, and also to measure the distance dependence of a small bar magnet at different points and compare those values. The results of my experiment were that N was found to be negative 2.9583 meters, and the magnetic dipole moment was 2.11 amp meters squared. So the physics concepts that were important in understanding this lab was the Biot-Savart law, and this is just used to find the magnetic field of a dipole, and then the distance dependence equation, which can be written in the two forms shown at the bottom. The procedure for this lab was to first download the magnetometer app on your phone, and then locate the magnetometer chip on your phone, and then line up the phone to compensate for the magnetic north, which is where the x component of the magnetic field is closest to 0. After you have them aligned, you're supposed to measure the distances where the magnetic field was equal to multiple different values, and then record the magnetic field magnitude of those distances. Here is the data that I found. The top left part is the data from where the magnetometer is on axis with the magnet, and then this data was graphed, which can be seen on the right, and from this graph, we were able to find the N value from the slope of the line, which, as I stated earlier, was found to be negative 2.9858 meters. And then at the bottom of the screen, you can see the off-axis values, and this was measured at that spot 45 degrees off the axis. Some observations from the experiment and the data was that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And when the magnetometer is far from the magnet, the x component of this is 0. Some calculations to define the magnetic dipole moment were that I got this top value from the y-intercept of that graph a few slides ago, and then I was able to find the k value from there and then plug it into the formula shown at the bottom. From there, I was able to find the dipole moment is 2.11 amps meters squared. Then moving on to my GlowScript model, the first thing I did was create this function to find the magnetic field of the dipole. I basically just translated this Biot-Savart law into the Python code here. And then this part of the code shown on the left is creating arrows for the on-axis magnetic field. The code on the right side of the screen is creating arrows for the perpendicular magnetic field. And then you can see that the on-axis arrows are shown in purple and the perpendicular axis is shown in cyan. Finally, we're creating an off-axis field, so the field from that 45-degree angle from that axis, and that arrow will be shown in green. Here is what the model looks like, and as you can see, the purple arrows are on the axis, and the cyan arrows are off-axis. There are actually 4 different arrows that are off-axis, but you can only see 3 of them because the 4th one is directly behind the one shown in the middle. And then the green arrow is in the corner, and that is the 45-degree angle. And then here's the output from our GlowScript model, and the part that we are most curious about is the magnitude of B at that 45-degree angle. And so the Python model found it to be 2.411252 times 10 to the negative 5. And then comparing that to our data from the experimental model, we see that it's quite different from in the experimental model. They're in the same order, so you know that you're on the right track. However, they are different, and that's because the GlowScript model only accounted for the magnetic field coming from the bar magnet, where in reality, there could have been other magnetic fields from other electronics or materials in the room that could be pretty similar, or that could produce magnetic fields that would interfere with the field and the bar magnet. So that explains the difference there. And finally, for the reflection questions, if I hadn't oriented the experiment to compensate for the magnetic north in the beginning, how would it be different? So accounting for the Earth's magnetic field makes the x component start at 0 teslas. And then that ensures that the field coming from the bar magnet. So if we hadn't done that, then the magnetic field from Earth's magnitude would be interfering with our results, and the x component would not start at 0 teslas, so we would have a different result. And if you were to stick two identical magnets together, the measurements would differ because the magnitude would be greater, but the direction would still stay the same.